Okay, good morning. So this is our last recitation, and no one's here. Let's see how it goes. We're talking today about minimization. We'll go through two algorithms of minimization for univariate functions. After that, we'll talk about some hybrid method. We're gonna talk you're gonna only talk about it without the algorithm. And after that, we will talk about the downhill syntax method for multivariate function minimization. Also, we will not go through the algorithm in detail, but we will talk about the notions of the idea. Okay, so our goal, for example, at first for univariate functions, to find some minimum and some range of the function. Now, this function might have a minimum there, or it might not have a minimum in the sense of, no, I'm sorry. If a function is continuous, it must have a minimum, but that minimum it can have a local many local minimas and many local maximas, and it will have also a global minimum and global maximum. So the problem of finding a local minima is much simpler than finding the global minimum, and we always in many algorithms, we always are susceptible to converge to some local minima when we seek the global. So that's something that you should know and should be aware of. And of course, if you want to find the maximum of a function, you find the minimum of minus that function. And as you know, finding minimum is like finding the points where our externals. It's like finding the points where the derivative of a function is zero. And because of this, you will find many algorithms that are for also minimas and maximas, and also for root finding problems. So in our recitation, we will take the hope, and we will assume that in our range that we're seeking in, there is one minima, and we want to converge it. So when do we have this this assumption as true assumption? It is true or correct with convex functions. If the function is convex, if the function is like that, this is a convex function. A convex function is a function in which, if we take any two points, the values of the function are under the straight line connecting these 2 points. This is a convex function. So in convex functions, if we take a range, there is a global minima in that range. It is for sure. And our algorithms will converge to that global minimum. And if we take another function, non-convex function, we're not sure that we go to the global minima, and we may be stuck in some local minima. But we will not think about that. We will think about our minimization, that it's good, and let's take the algorithm as it is. So if we want to find a global minima, it's called optimization. That's the name of it, optimization problem. And if the function that we optimize for it is linear in its variables, and there are some linear restrictions, we call this linear optimization. And If not, we call this nonlinear optimization. So we will talk about nonlinear functions, but we will assume that we have a minima there that we will converge to it. And let's think about the simplest two methods. So the simplest method is to start with some range, AB, some section, and take a smaller section of that section and try to shrink the interval as we can. So let's take let's think about it like this. If we have a section or an interval A and B, so we can ask about two other points. I will call them C and D, and check the values of the function here in C and D. So again, I'm assuming that the function is convex. I'm assuming that between A and B, the values here are lower than the value at A and the value at B. And if I have evaluated the function in C and D, if f of C, so I am seeking the minimum between A and B. Now, if I found that f of C is less than f of D, what do you think? Now I can say that the minimum lays in which interval? I want you to share a little bit.
Maybe A through D.
Yes. So if f of C is less than f of D, I will say that I will seek now between A and D. That's my new interval. So this is one iteration in my algorithm. My algorithm, one iteration that I take 2 points in between and check if f at C is smaller than f at D, I will take the new interval in the next iteration to be A and D, from A and D. And if f of C is bigger than f of D, now I think that the minimum is between C and D. Yes? And because I'm talking about iterations, so this is the iteration number I, so I call all of these i's. Okay? And this will be the AI plus 1, BI plus 1. And this will be the AI plus 1, the BI plus 1. In each iteration, AI, in an iteration AI, BI, that's the interval that I start with. So now I will fix the method for me to get C and D from A and B, and I say that this and this are equal, and the length of them is rho multiplied by BI minus AI, where rho is less than half. This is rho multiplied by BI minus AI. So in each iteration, I get to in the first iteration, I get some A and B. These are the A0 and B0, or let's call them A1 and B1. And I calculate C1 and D1. What is C1? For example, if you fix rho to be a quarter, so the C1 is A1 plus the quarter of this section multiplied. That's it. So it is AI plus the quarter of this section. and the di is bi minus the quarter of this section, and I evaluate the function at c and d, and check if f and c, if f at c is less than f at d, then the new section, the new interval that I think the minimum place there is a and b. And if this is smaller than this, I will think that I will fix, or I will determine that the new section of iteration of the next iteration is between C and B. So the C and B will be the AI plus 1 and BI plus 1. Any questions about this? And if there is a minimum there, if the function is convex, it is guaranteed for me to converge to that minimum, and the length of the section at the iteration number I, what is it? What is the length of the section I start with in iteration number I, number n? Yes? Are you with me?
bi minus ai minus 2 times rho, but I don't think I get you there.
So you have to remember also that this is 1 minus 2 rows multiplied by di minus ai. Yes? So in each iteration, I have some length, and I make it smaller to what? To 1 minus rho multiplied by that. Yes? So if I start with b minus a, after I iterations, I will go to a section with, it is 1 minus 2 rho plus rho, it's 1 minus rho to the power of I. Yes? So that's and convergence is guaranteed if the function is bounded. Yeah. Any questions? So it's a simple way. Now I add to this way, and that's why we call it the golden section method. I add another consideration. When I calculate here, and let's say that I found, let's say that a and b equal b minus a equals 1. Okay, let's say that it equals 1. So I'm talking about the first iteration, and let's say that this is 1, and this will be rho, and this will be rho. This will be 1 minus 2 rho. 1. Now let's say that f of c is smaller than f of d, and my new iteration will be in a and d. Okay, so this is a1, b1, d1, and c1. Okay, let's take them in black. Now, in iteration 2, this will be a2, and this will be b2. The d1 is b2. And now in this interval, I will take rho multiplied by the length of the interval. What's the length of this interval?
1 minus rho.
Minus rho. So I will take rho multiplied by 1 minus rho, and this will be the new d, so this is d2. And from the a1, I will take rho multiplied by 1 minus rho. And this will be the c2. Okay? Are you with me?
Yes.
Oh. Now, I have to evaluate the function at D2 and at C2. If one of these points is C1, so I have evaluated this this value before. So that's my new consideration. So our way works for every row. Now I will choose some row that makes this happen. That I will not the evaluation that I will do for the function is only for one new point instead of two new points. Okay, so I will ask for D2 or C1 to be equal. I'm sorry, for D2 or C2 to be equal to C1. Yes. So I want the C1 minus A1 to be equal to the C2 minus E2, which means that rho will be equal to rho multiplied by 1 minus rho. And this cannot happen. Okay. So rho will be 0. Okay. And I can ask, this is one possibility, and the other possibility, I want that D2 minus A1, D2 minus A1 equals to C2 minus A2. So what is D2 minus A1? D2 minus A1 so if this is rho multiplied by 1 minus rho, all of this is 1 minus rho. Yes? And this is rho multiplied by 1 minus rho. So this is what? 1 minus rho squared. Okay? So that is 1 minus rho squared equals C2 minus A2, which is rho multiplied by 1 minus rho. Okay? So if we solve that, we will see that the rho will be 3 minus the square root of 5. The plus is bigger than half, so we'll take the minus square root of 5 over 2. Okay? That will make this point is this point. Okay? Questions?
Muhammad, it just make it easier. So a new point will be point that we already know, so we don't have to calculate it.
Yes. So my new 2 points, one of them will be the C1 that I evaluated for before.
Okay.
Okay. So again, my way or my method works for any row. Now I choose a specific row that makes the number of calculations smaller. It's the half. Okay. So now in each iteration, I will evaluate the function for one new point because the second point I have evaluated for it in the previous iteration.
These do not appear to be the same equations. Here we have 1 minus 2. We don't have that on the board.
What?
In the recitation papers, we have an equation A2 minus A0 equals to 1 minus 2 rho. Where did we get this?
And here they call the A2 what I called the C2. Okay.
Okay.
So I prefer my notation because It's a better notation, okay?
But we don't have the same set of equations.
It's again, in row, it's the same equation.
Okay. Um,
Other term wrong. Ah, okay.
it appears that the solution to your set of equations is half in the second equation.
Yes, let's see. Yes, let's look at it. I see. Ah, okay. I I wrote here C2, it is C1. C1. And this is row now. But now the row, yes,
Yeah.
but now the row will be the golden ratio, and also this is not true. This is 1 minus 2 row. Ah, it's good. Okay.
And the equation in black, the solution to it is only 0. That's
Again,
also good. And the equation in black, row equals row 1 minus row. The
yes.
only solution to it is 0, right?
So I will not take it. And it is obvious that the C2 cannot be the C1, because the C2, it is row multiplied by 1 minus row, and the C1 is row. So that's
Oh,
why.
right.
But it can be that the D2 is equal to C1.
Okay. Thank you.
So it's some cross. Okay, so the D2 will be the C1. I will go to the other side because of that specific choose of the. Okay, and we call it the golden method, or the golden section method, because not because of a golden triangle, but because that this equation, this section at all will be divided to using that golden section. So if you remember, the golden section is 1 plus or minus square root of 5. So this is the 1 over 1 minus row. So if we take all this divided by all this, it will be, so from A0 to B0 divided by A0 to B1, it's the same that we divide A0 B1 to B1 B0. So if we write the equations in another way, using 1 minus row, not using row, we will see that the golden ratio, which is 1 plus square root of 5 divided by 2, will arise. Okay, so it's like this. Okay, so that's the way that's the reason why we call it the golden ratio. And when do we stop? That's the question. So when we make n iterations, we can continue. We will we will determine some terminating point. Okay, so where is this termination point? The answer is you can choose that when you get to a very, very small range, okay, when the A and B that you get, you shrink and then you shrink, you shrink, you shrink. When the A and B you get are so close to each other, so you will stop your algorithm. So that is something we can say if this is smaller than some error, we will stop. But we can also say that I want that when I evaluate the function and compare it in our method, we compare the evaluation of the function, yes? And I compare it to another thing, I will ask for the difference between them to be so small. Okay, I can ask that f, let's say of bi in some iteration minus f, let's say in di, it's the point in between, is less than epsilon. Okay. And you might think that the x will be the x that you find will be far. So let's say that this is the minimum, and the x you will find, you might be tempted to think that it's far from the real x or the real minimum by some accuracy of the machine, but it's not it's not sure that that's the way the thing, because maybe the function have very small value, very close values, and this is the way that you should think about it. So if I choose this, I might choose both of them, by the way. I might choose both of them. But if I choose the second one, and usually we choose the second one, then the error of x, will be somehow related not to epsilon of the machine, but related to the square root of epsilon of the machine. And why is that? I know that you're seeing what's written in there. The reason of that is that the function here near to this, if I'm really near to the minimum, the function here is behaving like some f0 plus 0 plus the half of n double prime at the x star, x minus x star squared. So if I want the function to variate here smaller than some epsilon, then the x will be far from the x star, smaller than the square root of it. Okay, so we and again, if this number is much smaller than the square root of epsilon, or much bigger, so we're talking about special cases. But this is the way to think of in general, that I don't expect myself to be far like or proportional to epsilon, but proportional to the square root of it. Questions?
Muhammad, why do you write f of bi minus f of di?
Where is that?
The second equation that you wrote on the board.
You can think about the values here. So the values that I've computed in my iterations are for the B's and the C's and the D's. and the A's. So it doesn't matter which points you take. Because I'm taking the DI at the end of any iteration, I will take the minimum to be, for example, the midpoint in the section, or the D in the section, or the C in the section, because I'm shrinking the section to a very, very small section. Yes. So when you get to the section that you want, it is very, very, very small. You will take any point in it. For example, the mid, or the D there, or the C there. So I took the D. Okay.
Okay.
Anyway, when you are so close to the X star and you chose your termination point rule, so it doesn't matter if you take the C or the D, you are there. Both of them will satisfy this or this. Okay. So if we are taking this function between 0 and 2, for example, and we want the size of the section to be 0.3, so it is sufficient for me to do 4 iterations. Yes, because again, bn minus an is 1 minus rho to the n, b0 minus a0, and it is sufficient for. So as you see, this is the golden ratio minus 1. Okay, so 1 minus rho is the golden ratio minus 1. And again, if I want this to be smaller than 0.3, I will have to take only 4 moves, and this is an example for the moves. Again, I start with 0 and 2, and I'm shrinking now. Okay, any questions? Okay. And if I'm talking about this parabola, it's squared between minus 10 and 20. So that's the parabola. I start, for example, from A and B. And I take, for example, this point. Now I'm taking this point and another point here. And this point seems to be smaller than this. So I will take this point and this point. Okay. Now, you see, this is the left point between the 2 new points, okay? The other point I don't draw, okay? Are you with me? So this green point and another point were here, and the green is less than the other one, so I chose the green. Now, the green that was here, the left point, is the right point here, and the other point is here. So that's what we say, that the D2 is equal to C1. Okay? So this is C1, and this is the D of this step, and the D2 is equal to C1, as you see. And this is C2. It lays here. And it seems that this point again is less than this. So the new section now is from here to here. And this is my point, and this is another point. And again, this point is smaller than this. So I choose my new iteration to be from here to here. That's the new iteration. And now, again, this point seems to be smaller than this. So my new section is from here to here. This is from here to here. And now, because I'm from here to here, this is the point, and this is another point. Okay, I'm sorry. This is the green point. So this point is smaller than this. Okay, this point is smaller than this. So I choose my section to be this. And now I have another point here, and it seems that the green one is smaller than the other one. So my new section is here, and we continue to shrink after we get to some very small region. Okay. So any questions about the depicting graph in here? Oh. So now let's talk about another way of calculation. It's the parabolic search method. As you see, our way is gets to a guaranteed solution, but it might be for you, say, not efficient or too slow. Now we can think about another way, which is the parabolic way. If I think that the function is parabolic in the region that I'm in, so I can choose to talk about 3 points, not 2 points, not A and B. I will talk about 3 points, A and B, and some midpoint. It might be A plus B over 2 in the first iteration, but after that it will be another point that we will calculate. Okay, so what is the parabolic way? The parabolic way is so easy. We start with, in each section we have 3 points. In each section we have x1, x0, x1, x2. So that's the A. So in the first iteration, we have A, B, and the x1 will be, for example, the A plus B over 2. When we have x0, x1, x2, we evaluate the function there, and we interpolate to a parabola. And after we interpolate to a parabola, we find the point of the parabola, the extrema of the parabola, and we call it x3. That's it. So if I have, for example, these values, that's the A, B, and C. I take an interpolation, and here I have now the x3. So this is x0, x1, x2, and now this is the x3. Okay, and again, I'm assuming that the function has the form of the parabola in the region, and I'm assuming that also the function is somehow convex if it's parabola, so it's convex. But first of all, I assume that it's convex and I have a minimum there, and after that, I assume that somehow it's like a parabola. And now, when I have x0, x1, x3, and x2, for the next iteration, I take the point to be the smaller point. That's it. The three smaller points. So here I will not take the x0, for example. I will start with x1, x3, and x2. Okay. So I write down this in some in the formula sheet. I've written it in some summary. Yes. So the point I call it x here. So in each step I have AI and BI and XI. Okay. In the first step I have the A0, AC, A0, C0, B0. Okay. And in each step that I have AI and CI and BI, so the C0, for example, is A0 plus B0 over 2. In each step, I will calculate from this the X star I, which is the extrema of the interpolated parabola from these 3 points. So that is the XI. Okay, you can you can find the formula of the interpolation and then find the minimum there. That's the minimum. The minimum of the maximum. Because this is the external of the problem. And now if you know that the xi between C and B, so here, for example, x3 is between x1 and x2. Okay? So if it's between them, so you will know that the section that you will take is here. Okay? And when I write down these 4 points, these four sections are detailed. Are the details of the determination that always I will get to some section A0, C0, B0, such that the C0 is between the A0 and B0, and the function in C0 is lower than the function in the ends of that section. Okay, so these for what demands of in my algorithm are to guarantee for the next section to be at AI, BI, and CI that behave like this, because always I want to be with 3 points that are like this. I want this point to be between them and this point to be lower than both of them. Okay. Okay, so okay, so here is another example of minimization, but using the parabola interpolation method, parabolic interpolation method, and now you can think that maybe we go to some maximum, not minimum. For example, if that's the function, and I chose my 3 points here, I will go to that maximum after some iterations. Or if I chose my 3 points here also. If I chose my 3 points here, you see, then the parabola that connects the 3 of them is this. So this will be, for example, a new point, and now I will talk about these 3 points. Again, always I will talk about the new point with other 2 points. Always I will take the new point. Let's see here again. And sorry, let's see here. Always I will take the new section to have the new point. Always the new point with the 2 other points. Okay. So this way I will get to some maximum, and and again, because I run away from the minimum, it might also that the function goes like this, and there is no maximum also, so it will not converge. So my way, this way of parabolic interpolation has these 2 disadvantages. So that's where comes the Brent's method. The Brent's method says that we will not go in detail in Brent's method, but it says that in each iteration, I will try to make the parabolic interpolation and find the xi star, but if the xi star is somehow outside the region itself. So I will say that the parabolic interpolation fails, and I use the golden section method. Okay, so it's some hybrid minimization method between the golden section and the parabolic interpolation, the successive parabolic interpolation. So we will not go in detail in Brent's method. We will only say that but I encourage you to write to check them. So that's the problem that I say that it fails. If it not only fails, but I also add the shrinking condition. So when I use the parabolic interpolation, I reject it and go to the golden section method if the new point is far from it is outside the range, or that this new point has an improvement of the previous points less than the half of the last improvement. Okay, and that's my way of rejecting. That's my way of guaranteeing that the process will converge. Okay, so if my new move is not less than my new improvement is not less than the half of the last improvement, I will reject this method and go to the section golden method, which will shrink for me the interval, where it will make it smaller. So always I will make improvements in my section. Okay. So that's the Brent's method. Okay, any questions?
Wait, Muhammad, I have a question. Can you maybe go back to the four conditions with the xi minima?
So these are the four conditions. These are
No, not this. It was another.
yeah.
Yes. So how, like in the second condition, for example, how does f of xi star is larger than f of ci? Like xi star is not the minima of the function. This is how we calculate it.
I know that it's the extrema of the function. I know that the x star, and because of that, I might not go to the minima. I might go to the maximum. So this parabolic method will find me an extrema, or it will not converge. Okay. So that. Okay.
Yes, thank you.
And this is a problem of it that I've explained and write it here. So the parabolic method simply requires that the derivative of the function is here. So it treats minima and maximum and inflection points the same. Okay. Okay. And now at last, I took this from Wikipedia. And again, we will not go much in detail, but when we have more than one variable, what's the difficulty there? What makes the problems of more than one variable much harder than the problems with one variable? Do you know? Have you thought about it? It's not written here. I'm asking you. What makes the problem of multivariate functions much harder than the univariate functions?
Finding the minimum of one variable is not necessarily the minimum of the function.
What?
I'm saying finding the minimum of one variable is not necessarily the minimum of the entire function in that section.
Yes, but when we think about numerical algorithms, what the main thing that fails with multivariate? The main thing that will fail is that the edges of the region that I'm talking about now are not 2 points. There are infinite points. Yes. So when we talk about some region for a univariate function, so the ends of the region are 2 points. That's it. But for two variables, if I talk about some region, the edges of the region are infinite points. So I somehow, in order to know that there is some minimum or maximum here, I have to think about this infinite points. So the algorithms with multidimensional minimization are, let's say, much complicated and less guaranteeing that we have a solution. But we'll talk about what's called the downhill simplex method, which, if we are, for example, in 2 dimensions, if we are in 2 dimensions, we will talk about some triangle. So we start with a triangle. Which is the region that we will check. Okay. And this triangle, I will check in it 3 points. Okay. And I will change this triangle using some algorithm that I copied here. Look. And the algorithm in its basic thing, it will take this triangular and try to reflect it. For example, to take this point to here, and that's my new triangle, or try to reflect it and expand it. Okay, and it will sometimes try to shrink it, or to contract it. Sorry, to contract it or to shrink it. So that's in 2 dimensions. And in more than that, we are talking about a simplex. The simplex is the generalization of the triangle. So simplex in n dimensions is some body in we call it polyton, but it's somebody in the n+1 dimensions, the n dimensions, that has n+1 vertices that do not lay in 1 dimension or 2 or 3 or 4 or up to n. They are in n+1. So one way of getting a simplex is taking a point called x0, for example, and take lambda I ei, where the ei are bases of the n-dimensional space. And let's see, for example, let's see, for example, two things in this algorithm. First of all, I order the points from the smallest value to the largest value, and I calculate the if this is the bigger value, this is, let's say this is the high, and this is the low. And I don't take the high and I call this XO, which is the average of the points that are not the highest point. Okay, and I call this the centroid of these points, except it's n plus 1. Okay, and now I will use reflection. This reflection will be that the highest one. Okay, so this is the highest point. I'm looking after the minimum. Okay, so because this is the highest point, I will try to take another point. Okay, so first thing that I do, I reflect this point to here and check the new point. Okay, so the first thing I do, I reflect it. This alpha usually is taken to be 1, but you can choose whatever you want. And when I reflect it, if this point is between this and this, okay, then we replace this point by, that's it, because it's smaller than this and bigger than this. So I drop this high point and take this. Okay. Now, if the point here that I reflected to it is smaller than even the lowest, I do not take the point itself. I take a contracted point. Okay, not a contracted, expanded point. So let's say that this is my triangle, and I somehow check this point, and it's lower than this, so I check also this point. Okay, so I make expansion, and that's my way. So you will see that you'll see that the things that we do, or the variations that we do to this simplex are somehow understood, and also the contraction thing and the shrinking thing are similarly understood, and this way will converge at the end. I'm suggesting that we see somehow something. Let's go again to the. You will see it's now for testing functions for optimization. So, for example, for this function, so we start with some triangular, and this triangular goes somehow to the minimum with our weight. Okay, so we start, we shrink, we reflect, and then contract and shrink. So you see also contractions. Contractions are taking all the points to some point. I'm sorry, taking one point to closer to others. It's like the expansion, but with a coefficient which is smaller than 1. That's the contraction, and the shrinking is taking all the points closer to some point. Okay. So this is another function. Okay, so that's the method, or visualizing the method, the visualization of the method in 2 dimensions. Okay, but the idea is the same in any dimension. So we always calculate all the points, and then take a new point, which is the reflection of the maximal point, of the highest point, and after the reflection, we check many things. Okay, and we might expand, and we might contract. Any questions? Okay. So again, that's it for today. And when is the exam?
It's in the beginning of April. I don't know the exact date.
Okay. Well, if you want, we might take some hour before that if you want. And you have seen this is the formula sheet. It's already on the model. And also you see in the model that there is a sample exam. So I think it's a good sample exam. You asked me before about the exam, so here is a sample. Any questions about anything in the course also? I'm moving here in order for you to see if you want to ask about something.
Will there be an assignment for this week?
Will be what?
For this week, finding minima and everything.
Is this included in the exam? Are you asking?
No, I ask whether
there's
we
not-
have an assignment about
Yes.
these subjects.
It's a simple assignment, yes. It's already on the Moodle.
Okay, and what about besides calculating numerical methods by hand, do we have to know code and things like that?
So the answer is yes, but it's not too complicated. So because of this, you have a sample exam. You can check it.
Okay, thank you.
So again, it's not. I don't know if to say it's not too hard because everyone sees things as he sees or as she sees. But you can check the sample exam. The answer for your question is yes, you have to know how to code, but it's not so complicated. So you will see questions that ask you to type a code. Yes.
Does the sample exam is in the same level as the exam itself, or is just for seeing the?
That's the spirit, but the but the exam itself is not prepared yet. But that's the spirit. I think.
Okay.
So, again, questions like this, you can ask Renan straight away. It's better than asking me. Okay. So, okay. See you before the exam and in the exam.
Thank you, Muhammad.
Thank you, Muhammad.
Welcome.